Hey hackers, Blue Cosmo from CCS here. Welcome back to the channel. Now, I have a question for you guys, right? If you came across this cipher for whatever reason in the wild, how would you go about decoding it? Now, it's a code. When I say cipher, I mean code specifically, right? This is a one-to-one code. So, like the letter A could be a square, and the letter B could be, I don't know, a circle, right? So, if there is some sort of one-to-one code for this code right here, how would you decode the code, right? Go ahead, take a second. Take a second to actually think about how you would approach this. Pause the video and try it. I'm serious. And leave a comment on like your approach to tackling this. I asked a few people about how they would, go about decoding this, and a lot of the response was mainly I don't know, and and I mean, y'all should try. Like if y'all don't know, that's fine, but make the effort to try. But second of all, I got some other responses, right? So one approach people brought up was like, let me shorten the cipher. Let's just do a triangle, a square, circle, circle, right? Let's say I'm just shortening this, right? Let's say we come across this one instead of this one up here, right? For whatever reason, people would do A, 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 and then they would go A, B. And eventually, I mean, you would get, all possible four-letter combinations all the way to quad Z, right? So, I mean, yeah, this works, right? But there's something I feel like people like miss every time they see this, right? When we look at a code like this, we see a triangle, a square, and two circles, right? That means if this is a one-to-one code, that means if these circles are, let's say these circles are B, that means both of these must be a B, right? Or if these are A's, then both of these must be A. But that also means that this square and this triangle cannot be the same letter as those circles. So the quad A can never be this code. This has to be a different letter. This has to be a different letter. And these two letters have to be the same letter, but different than those two, right? Because it's one-to-one. So instead, what I would think would be an appropriate approach is to create a code transcript of the cipher. Let's say we have this short code right here, and you want to get the code transcript of it. A code transcript is just letter representation of this code, right? Obviously, you couldn't type this up into a computer, right? These are non-ASCII characters, right? You couldn't just type it out on your keyboard. So instead, to make it easier for cartographers, we just represent each of these symbols with a letter, right? So let's just go down the alphabet, right? We'll represent this triangle with an A, this square with a B, and then this circle with the C. Now, because the circle has already existed before within this cipher, we'll use the C again to represent this code. So now we have a more accurate representation of our code here, right? A, B, C, C is a little bit more accurate than a triangle, square, circle, circle. So from here, we could actually just shift each of these characters down, keeping the same characters throughout the shifting, right? So let me clarify, right? So let's say if we wanted to shift this down the alphabet, right? So we'll go to the next highest order, which would be A, B, and then instead of CC, we want to go down to D, D, right? So we can continue this trend, right? We go E, E, A, B, F, F, all the way to A, B, Z, Z, right? So now we have A, B, Z, Z. So now if we wanted to go to the next highest order, right, we wanted to see what happens with all iterations of this B being a C, right? So we'll have A, C. So these next two letters, right, they couldn't be A because A is right here. And this triangle is not the same characters as these two circles, assuming that it's a one-to-one code, right? So this couldn't be AA. So it would have to be AC, B, B. But now, when it goes up to the next iteration, it couldn't be AC, CC because the C is already being used here. So it'd have to go to A, C, D, D, and then it could continue on the alphabet, right? So then you get to A, C, Z, Z, and then the next iteration, right? That would be A, D, and it couldn't be AA because we already have A as our first index. It could be BB, and then ADCC, and then it couldn't be ADDD because we're already using this D here, so it would go to AEE or AEF, F. Whoops, ADEE. There you go. My apologies. So you guys kind of get the idea now, right? So using this iteration will give us all possible combinations of what this transcript could be, right? This technically gives you all combinations of what a 4-letter word or character or 4-letter string could be. But it's not accurate because these two characters, none of these examples I showed here could ever be this code because these codes are 1-to-1, right? This could be, let's say the word is ball. Let's say it's B-A-L-L. Let's say that's our plain text, right? So if this is our plain text, our ciphertext would be the triangle, the square, and the circle, right? And you again notice that these are all 1-to-1, right? These two circles share both of those L's. And then this B represents that triangle and that A is that square. So with that knowledge, that means that the possible, like A could never be this code, all right? So yeah, hopefully that kind of makes sense. So now let's go back to our original approach, right? This is the original code. So if we look at this, we'll notice that we have, first of all, a triangle here, and a triangle here, and a circle here, and a circle there. That means that this triangle and this triangle must be the same letter, and this circle must be the same letter. Again, assuming that this is a 1-to-1 code of letters, right? So then that means our code transcript would be A, B, C, and then now, because we used this triangle before, it would be A again, right? Because this triangle is ready to be represented by A. Then it would be D, E, F, and then this would be C because the circle has already been used before as C, and then it would be G, right? So that would be your code transcript for this cipher. Let me go ahead and open up a new page. Okay, so I've moved our code and our code transcript over to this page right here, just to make it a little bit easier to kind of interact with. Now, again, let's go ahead and use the same shifting process throughout our code, right? So let's say if we wanted to go to the next highest order of this cipher, right? So we're going to start from G, and we're going to move all combinations of this with the last character being different, and then this with this character being different, this with that character being different, and so on, right? So our next order would be A, B, C, A, D, E, F, C, H, right? And then this would be I, J, K, all the Z. Let's say we have our last characters go all the way down to Z, right? So we get A, B, C, A, D, E, F, C, H, C, I, C, J, C, K, all the way to C, Z, right? I'll go ahead and attach that. So we get all the way down to C, Z. So now we want to get the next highest order, which would be this character going up to the next character could be. But it couldn't be D, right? It couldn't go from C to D because this D is already being used in our code transcript. So instead, it couldn't be E either because this E is being used. It can be F. So then this would have to be a G. So then it would be A, B, C, A, D, E, F, G, and then this couldn't be an A either because A is being used. Couldn't be B, couldn't be C, couldn't be D, couldn't be F, couldn't be G. Has to be H. So that would be the next highest order sequence of characters, right? I know it's kind of complex kind of think about, but it's pretty simple, right? Again, it's just the same thing we were talking about, but just with a lot more characters, right? But what is this doing, right? This is just getting all possible combinations of what this code could actually be, right? This, again, like I said, like you could just do A, B, but that wouldn't work, right? Because this code could never actually represent A, right? Because they're all different characters except for the shared characters in between them. So eventually we would get the actual word, right? If we go back to this example and have our triangle, square, circle, using this method, we would eventually get words like ball. We would get words like fall, maybe bass or bass, right? A lot of 4-letter words, but again, they're all 4-letter words that share the same two last letters because these two circles are the same letter, right? So with something like this, we could only pull out actual letter combinations that fill out the same format. So because of this, right, we would actually get the word SUBSRIBE, subscribe, right? Obviously, I know that was a lot just to make a point about you should subscribe to the channel, but also to kind of point out some interesting concepts about codes like this, right? So obviously, it would be really cool to automate this, right? And I did. It took 2 months to automate this program, and yeah, it took weirdly long. But I want to talk about some stuff before I show you the actual program. Let's just talk for a second. Let's talk for a second, right? So let me use this short example again. Just this triangle, square, circle, right? So again, we come back to this code transcript because it's just shorter than this one. But I mean, this could be a mere trifecta of things. Is that the word, trifecta? All right, so let's talk about a few things about this entire concept because it's not perfect, right? This ideally works, but there are some cons to it, right? First of all, we are assuming that this code is a one-to-one 26-character code, right? But what if this triangle right here was actually representing the number one? Number one is actually equal to triangle. And then they have codes for all their numbers. So number 2 could be circle, number 3 could be square, and then the letter A could actually be a diamond, right? Like, they have other shapes for more characters that are inclusive into our actual code that we're working with. So how do we go about fixing that? Well, it's actually pretty simple. We just account for additional characters that are in the code into the code transcript. Now, obviously, we wouldn't know that at first hand. I mean, technically, you could just analyze the ciphertext and kind of figure out some characters different than the other. I'll show you guys some examples throughout the video to kind of get you guys to understand what I'm talking about better. But ultimately, like if this was like a number 1, this could throw the entire cipher off unless if we accounted for numbers in the code transcript. So let's say instead of A, B, C, C, right? When we shift down the alphabet, so we'll go to A, B, D, D, and then we'll eventually go down, right, to A, B, Z, Z, and then we just do A, B, 1, 1, right? And that's us accounting for numbers now. So now we can do A, B, 2, 2, and then just continue that process. That's what we need to do if we need to counter numbers, special characters, stuff like that, if they're encoded. If they're not encoded, then we can just skip and ignore them. So that's the first thing. The second thing is, if we know part of the plain text, right? Let's say we have our triangle, square, circle, circle. If we know that these 2 circles are the letter L, that means we only need to account for this character and this character. So now we only have to iterate between these 2 characters, right? So now we could try A, B, L, L, and then A, C, L, L, and then A, D, L, L, and so on, right? And then eventually you would get the actual all possible combinations of those. Now, when I'm talking about filtering out words, right, it's not that hard to do, right? We just get these outputs and then we check if this output is in the English dictionary, right? Now, again, I'm assuming English for this, but this would work for technically any language, right? I would assume, right? Because if this is a French word, then you just iterate through the French alphabet as a code transcript and iterate through those letters instead. So yeah, this would work with virtually any language that I'm aware of. Not every, but probably the vast majority. And another thing we can also consider is like vowels and stuff too, right? Let's say if we have like triangle, space, square, circle, I don't know, heart, right? So let's say this is our code right here. This individual triangle right here, realistically speaking, according to the English alphabet, would only be an A or an I, right? That's the only 2 things it would realistically be, not including a number, because it wouldn't likely be O, because O is just not a word. O is like, you can say I have a cat, or you can say I am really cool, but you can't really say like O, like there's OH, but there's not just letter O by itself within the English language. So that's kind of stuff you can kind of consider as well. So the tool I'm going to be using for the remainder of this video is called Skeleton Key. Skeleton Key is a really cool cryptographic hacking suite created by myself, as well as a few other of the Cosmodium developers. I'd like to give a special shout out to Hayes, Soulsender, and Fizz, as they've been key people in making this tool happen. So huge shout out to them. But in order to install it, it's actually a really simple install. All we have to do is clone the repository, and I'll just go ahead and clone it. We can cd into the skeleton key directory in list, and we can see that we have a install.sh file right there. So we can just bash install sh and run it. Go ahead and type in your sudo, and there you go. So it will install skeleton key once it's finished. Okay, so now it's asking if we would like to reinstall it. We'll say Y for yes. And there you go, it's finished. So all you have to do is open up a new terminal. So I'll just go ahead, Control D, and then open up a new terminal. So now that we have skeleton key installed, let's actually go ahead and play around with it just a little bit, just so you guys can understand how it works. So we can look at the help menu by doing key tag help. And it shows us a menu of all the different ciphers that skeleton key is capable of doing, right? We can see Caesar cipher, Visionaire cipher, reverse cipher, etc. So each of these ciphers has their own little acronym, and that's what kind of denotes the cipher for skeleton key, right? So if we want to play around with Caesar cipher, we can look at the CC right here, right? So if we do key CC, it will show us the help menu for the Caesar cipher and all of its different arguments and stuff, which is pretty cool, right? We can actually go ahead and play around with some of those arguments as well. So we can do key Caesar cipher, tech E for encrypt, tech T for the input text, and we'll put in hello, and then we'll use a key of 5, right? So boom, that's how you can encrypt with something like the Caesar cipher using skeleton key. One thing is, like, I'm sure you may get annoyed by having to type in key every time you want to use skeleton key. So what we did is we made something called the key console. Basically, you can type in key, and boom, it puts you into this own console that has all the skeleton key libraries loaded. So we can do like help, and we can see that we have the skeleton key libraries already in here. So we can do like CC, and you already get this stuff for skeleton key. So you don't have to type in key every time you want to use it. So that is a viable option. Also, it does use terminal arguments as well. So if you want to do like list, you can do that as well. Cool. So let's go ahead and actually start playing around with the code transcript stuff. So right here, we can see my code transcript contribution that I made to skeleton key, right? And its acronym is just CT. So it should be pretty straightforward to follow along with, right? If we type in CT, we can see all the different arguments for the actual code transcript tool within skeleton key. But I'll kind of talk about how to use it anyway, so it's not too important to look at those. Actually, one thing that is important is you do need to note that this program can get pretty memory intensive. So definitely like keep your transcripts short. I don't want you guys crashing your computers and stuff. So, all right. So now that that's out the way, let's go ahead and start playing around with the code transcripts. We'll brute force the transcript ABCC, right? The one that we saw previously for the triangle, square, circle, circle. If we run this, it gives you it gives you a lot of output. It does, but there are words in here. If we want to, I'll go ahead and save this to a output file. I'll call this output.log. Cool. And if we exit and then vim the output.log, we can see all the stuffs in here, right? If I do slash like ball, for example, right? Ball's in here. Slash bell, you can see bell in there. Slash fall. And falls in there, right? So yeah, we can see all the words in here. But the one thing is, like, you don't want to manually search for all those words because that would be kind of annoying. So instead, what we can do is we can rerun our code transcript program, and at the end we can add a tag words, and this will just pull out all the words for us. So you can see it's getting words like gall, toll, pole, land, till, right? So it gets the words out for you. But yeah, it gives you like a word list. So if you guys want to have like a list of words you can use to like brute force whatever that code could be, you guys have it. But whatever that code is, you now have at least one of these being the right plain text for it, which is pretty cool. Something else skeleton key can do as well is we can actually attach known plain text. So if we do like A, B, LL, like that example we had earlier where we knew the last two characters were LL but didn't know what the first two characters are, you could do this as well. And all the lowercase letters are indicated as plain text, and the uppercase characters are indicated as code transcript. So we can actually do attack words on this as well and pull out all the words that end with LL specifically. Now that we have a good understanding of how my algorithm actually works, let's go ahead and play around with it to see like how effective it actually is. I have a challenge here, and it's called the WOW signal. It is a challenge from Space Heroes CTF 2022. So huge kudos for them for developing this really cool challenge. But I actually do have a video on this challenge and a write-up on this challenge, so I'll leave those in the cards or description if you are curious in checking either of those out. In the challenge, we're given two files, a signal.png and a woe.png. The signal.png re-emphasizes the theme of the challenge, showing what is quite literally the wow signal, right, dubbed after the words wow written right next to it. I think it has to do with some sort of like alien signal that was found in space or something like that. You guys can do your own research on that if you like. The woe.png is a document coded using some sort of alien language, but in the center of the document, you can actually see our flag for the challenge. We can tell it's our flag because all of our flags, at least for this CTF, start with SHCTF, an opening curly brace, some text, and then a closing curly brace. Since the document isn't coded, we can't directly see the SHCT or F part of this flag. But it does give us an advantage, right? Because now we know that all of those symbols must belong to SHCTF respectively. Now that we know all the characters that can be SHCT or F, we can plug them in and get our code transcript, where the lowercase letters represent our known plaintext and the uppercase characters represent our code transcript. So before we even use our algorithm, let's just use some like common sense, right? Earlier, I talked about how we already know that most, or if not all, English words have at least one vowel in them, right? Those being A, E, I, O, U, or Y. Seeing that our code transcript, or at least two words in the center of our code transcript is transcript C, plaintext TS, and plaintext TH, transcript D, we know for both of those words, the missing letter has to be a vowel, right? So the only possible words those two could be is its and the respectively, right? So we can actually just set this up in our new transcript and plug in any of the repeating plaintext characters throughout the rest of the code. Now we only have two transcripts left to decode, right? Let's start with the transcript ABA. And using skeleton key, we can just run code transcript, brute force the text of ABA, and then we'll pull out all the words. Whoops, words. Cool. So now we can see a bunch of words in here, and the one that stands out to me the most immediately is just wow. I mean, let's be real. The challenge is called the wow signal, and on top of that, we saw the wow in the signal.png filter that we looked at previously also mentioned the word wow. So plugging that in, this would be our new transcript, right? SHTF, wow, it's the, and then our new transcript. Now you'll notice that I do update the transcript every time we get new plaintext characters because the transcript must always start with A. So now our new transcript is transcript ABC, plaintext TI, transcript BD, plaintext S, right? And we can plug that into skeleton key. So let's go ahead and do that. We can type in CT, brute force text of this, and then we can pull out words as well. So this one's going to take a little bit longer, but it shouldn't take too long, obviously. I mean, it's an intensive program, but it shouldn't be too bad. So we can see I only pulled out 5 words that could be right. And this Martians one stands out to me the most because it's about space, it's about aliens. So Martians makes the most sense. But I mean, you could try any of these for your flag and see if it works. But we know that some of these can't work, like T, for example, because we already know all occurrences of the letter T within our plaintext. So we could use that and get our final flag, which is SHCTF. Wow, it's the Martians, which is the correct flag. Now, random alien codes isn't the only thing this algorithm can crack. Like I mentioned before, this algorithm can crack virtually any code, right? If we take my name Cosmo and we ran it through the Pigpen cipher, Morse code, @bash, and ROT47, we will get the following outputs, right? Now, all of these following outputs have the same exact code transcript of ABCDB. Now, if we go to my algorithm and we do CT brute force the text of ABCDB, right? And I won't save it to words, but I'll save it to like, we'll just do words.log. Now that I finished, we can exit and we can go on vim words.log. So now if I search for Cosmo, we can see Cosmo is a output of this code right there, right? So we can see that when we run that through my algorithm, it returns Cosmo as a possible plaintext output. So this just goes to show how well versed the algorithm is. But what about encryption? Again, up until now, we've really been considering codes, right? We haven't really dived into encryptions. Technically, this would work on the Caesar cipher. Actually, I'll show you guys an example of that right now. Well, this code can never crack something like AES or RSA, any modern encryption for that matter. But it's interesting to notice the ones it can crack, right? Like Caesar. The Caesar cipher is a very, very simple cipher. It takes a number key and shifts each character in its plaintext down the alphabet by that number. So if we go ahead and take Cosmo and encrypt it with a key of 5, right, we can do Caesar cipher, encrypt the text Cosmo, with a key of 5. And boom, our output is HTXRT, right? So it will shift our first letter C down the alphabet 5 times. So it'll go from C to D to E to F to G to H. So H will be the encrypted version of C. Now we go to our next letter O and repeat the same process for the rest of the characters, right? And shift it all the way down until we get HTXRT. But you will now notice our code transcript for our new output ciphertext of HTXRT, the code transcript is just ABCDB, which is the same transcript we use for the Pigpen cipher, Morse code, @bash, and ROT47, which means it also decodes back to Cosmo, right? So, like, it's funny, it's crazy, right? And it's a really interesting kind of thought. Now, although this works, obviously it's not the most ideal way to crack the Caesar cipher, right? Because the Caesar cipher shifts through the alphabet, right? There's only 26 possible shifts each letter could be. So if you just decrypted your ciphertext 26 times and did it with a different key each time, one of those outputs would be the actual plain text. I'll go ahead and show you guys that, right? So if we do Caesar cipher, brute force the text of HTXRT, which is the encrypted version of Cosmo, we can run this and you'll notice that at a key of 5 is Cosmo, right? So this is a lot more effective way of cracking the Caesar cipher. It just goes to show that even though you can do this, iterating through code transcripts also works, which I found pretty funny, right? If you want to learn more about like this kind of concept about like cryptographic hacking and strategies like that, I definitely do suggest you check out my lecture. I give a lecture to a club at a Polish University of Technology. It's called Breaking Ciphers, Picking the Locks of Cryptography. I'll be sure to leave it in the cards and description, stuff like that, so you guys can check it out. So now that we've gotten a good understanding of like how the algorithm works and stuff, let's actually take a look through the code and kind of get the idea of what the code is doing to make this entire process work, right? So right now we're looking at the ct.py, which is the code transcript.py code functionality of skeleton key. Now, this is just the help menu. We can skip through most of this. So when you run that TACB option, it actually executes this brute function. And this brute function basically gets all your arguments, your text, whatever alphabet you chose, all this other stuff. If you did choose a custom alphabet, it would just format the alphabet so that way it will work. If you actually added some input text, it would just format the text and run it through our decode transcript function as long as some other arguments and then output the returned output. One thing is if you do have the words argument checked, it will make sure to run it through this dictionary function at the top. And this dictionary function just sees if any of these are words output. But the actual main core of the code is in this decode transcripts function right here. It takes in an input of the transcript list. So basically it's just a list of all the transcripts. After that, we have our alphabet that we're using. Then we have a count here to account for the recursion. So now we just iterate through each transcript within the transcripts list, format them so we can get rid of any special characters, ignore the lowercase characters, which are the plain text characters and all that. But then we create a set out of it. And the set is going to not only remove duplicate characters, but it's going to allow us to do some like data analysis on the two sets, right? So we have a transcript set, which is the one that we're iterating through, and then the transcript set, which is like the universal one that you inputted. So the one that you inputted into the code. It's going to get characters that are in both of those transcripts by using that and sign. And then it's going to iterate through the alphabet and just basically replace those letters that are in both transcripts. And then once we do that, we're basically just saying, hey, get rid of any duplicates that we have made, get rid of them. And then output it as long as our count is equal to the length of the transcript, right? Because basically with this, you have to iterate through the alphabet 26 times for each time in the length of the transcript. I know that was kind of a mouthful, but if you follow along slowly, it kind of makes sense. If we don't hit that length, we're basically just going to recurse it by adding to our counts. And then we're going to take our new output and throw it back in. So it just recursively changes all of those letters until we finish the code. And that's basically it. When I say it took 2 months, it didn't actually take 2 months. It took probably like a week and a half, but over the period of 2 months is kind of what I meant. But yeah, thank you guys so much for watching this video. A lot of work came into this video, like 2 months of work actually have been delved into this video. I still have tons of footage of the development of it, but I figured there wasn't much of a point of including it. But so because I'm not including the footage, I do want to give a special shout out to Hayes, especially because he did try to help me with the program. I did end up making it myself, but he was there from the beginning, really trying to figure out how we can get this working. And he did make some key steps into me getting the final code working. So a huge shout out to him. But otherwise, thank you guys so much for watching. Really appreciate you guys. Make sure to leave a like, subscribe, share the content, Let's grow this channel as much as we can. But other than that, stay happy, stay positive, and as always, happy hacking.